Hello everyone, I'm Lujia. I'm going to tell you about our work, the MapperX. SSDs are preferable to HDDs in building cloud storage systems, as SSDs significantly outperform HDDs in random small I/O, which is dominant in the cloud. Since currently SSDs are still much more expensive than HDDs, in recent years, we see a trend of adopting HDD-SSD hybrid storage for high I/O performance at low monetary cost. For instance, URSA is a distributed block storage system which stores primary replicates on SSDs and replicates backup replicates on HDDs. And the SSD integrates a small SSD inside a large HDD, of which the SSD acts as a cache. As the demand of HDD-SSD hybrid storage increases, NiceX kernel has supported users to combine HDDs and SSDs to jointly provide virtual block storage service. DMCache is a component of the device mapper in the kernel, which has been widely used in industry to map SSDs and HDDs onto higher-level virtual block devices that take fast SSDs as a cache for slow HDDs. DMCache records the mapping between SSDs and HDDs for each cache block in its metadata. When DMCache adopts the default write-back mode, a block write will go only to the SSD cache and get acknowledged after being marked dirty, so that the dirty block could be demoted from the SSD cache to the HDD later in a batch for accelerating random small I/O. Consider a small write to a virtual DMCache device in the write-back mode. If the target block is already in the SSD cache, then as shown in figure, first, the new data W is written to the SSD. Then, the corresponding bit of the block is set dirty in memory, and then the write is acknowledged. The cache block will be asynchronously persisted to the cache according to the cache policy. There are two kinds of metadata. The metadata for the cache block's mapping between SSD and HDD already exists and thus needs no persistence, and the metadata for the block's dirty bit has to be asynchronously persisted. Because once being synchronously persisted, this update will be on the critical path of writing W, which would greatly affect the performance of cache writes. In original DMCache, the persistence of the dirty bit is not for crash recovery, but for graceful shutdown, which happens after dirty bits are persisted, so that up-to-date dirty bit metadata can be read after reboot. If the target block is not yet in the cache, then the processing is slightly complex. When the write is not aligned with a block, the block needs to be first promoted to the cache with the first kind of metadata being persisted, after which the processing is the same as cache block writes. Note that the mapping metadata must be synchronously updated, in which case the synchronous update of the dirty bit metadata is less harmful because the number of metadata writes only increases from 1 to 2. In contrast, if the mapping metadata needs no update, then the number of metadata writes sharply increases from 0 to 1. Mapping metadata updates is largely decided by the locality of the workloads together with the replacements policy. Generally speaking, higher locality of writes cause less changes of mapping metadata, which makes synchronous dirty bit persistence have higher negative impact on the performance of cache writes, and vice versa. To demonstrate the runtime performance problem of persisting metadata for each write, we compare the I/O performance of DMCache with synchronous and asynchronous updates, respectively. We use FIO to performance random writes and evaluate the IOPS with IO depth equals to 16 using various cache block sizes ranging from 32 KB to 128 KB. The FIO write sizes are the same as the cache block sizes. The results show that the I/O performance is severely affected when adopting synchronous metadata update. When the IOPS degradation of about 2.13 times to 3.42 times. The high runtime overhead prevents synchronous update of 30-bit metadata from being adopted by DM cache. Unfortunately, asynchronous metadata updates cause all cached data on SSDs to be assumed dirty once the system crashes and gets restarted, which results in long crash recovery times and consequently low availability. For example, in our production block storage system, where we use DM cache to combine multiple SSDs with multiple HDDs on each storage machine, it takes more than 2 hours to recover from a power failure, even if most blocks are clean. The low availability prevents NiceX HDD-SSD hybrid cache mechanism from being widely applied in available sensitive scenarios. The timing of 30-bit metadata update is a dilemma for HDD-SSD hybrid devices. The asynchronous update mechanism periodically updates 30 bits for not affecting normal writes, but suffers from long crash recovery time. The challenge is that there is no trade-offs for the timing of 30-bit metadata updates, because once the metadata is asynchronously updated, even only one updated bit state would require demotion of all cached blocks to ensure data durability after crash recovery. To address these challenges, our key idea is to adjust granularity instead of the timing of the 30-bit metadata updates to smoothly trade off between normal I/O performance and crash recovery time. Workloads in the cloud usually have adequate write locality, which can be leveraged to use one bit to represent the state of the range of consecutive blocks. As long as we can roughly know the effective range of the bit, know that the false positives of the effective range are not critical. If no clean blocks is wrongly included in the effective range of a 30-bit, the price is simply an unnecessary demotion of the block in crash recovery. There is an in-memory bitmap that precisely records the state of every block. We first extend the in-memory bitmap to a hierarchical complete bit tree, or CBT, where the leaves are the bits of the bitmap, and each inner node is the disjunction of its direct children. Then MapperX maintains a summary of the CBT on the metadata device, which we refer to as on-disk adaptive bit tree, ABT. The ABT is synchronously updated for each write request, but most updates do not cause disk writes for metadata persistence. Each inner node of the ABT represents a range of consecutive blocks, and thus only the first 30 block within the range causes a write to the metadata device, and the subsequently writes of blocks in the range leaves no persistence. For example, in this figure, the node A of ABT represents the range of block 0 to block 1. The node B of ABT represents the range of block 2 to block 3, and node C represents the range of block 4 to block 7. Initially, the ABT only has a root node representing the states of all cache blocks, which will change from clean to dirty after the first block write. Once a block's state changes, the CBT in memory has to be changed also, and it will be persisted in ABT. For example, in this figure, when the block 7 changes to clean from dirty, the leaf node of number 7 and its father and grandfather will follow to change to clean, and the node of ABT, which include number 7, should be persisted with a clean bit. MapperX possesses a synchronous ABT update mechanism, which can adaptively adjust the metadata persistence frequency. The basic idea is to control the corresponding bits of the leaves by adding or deleting the leaves in the ABT. Leaves at higher levels in the ABT represent the states of a small range of blocks, and thus increasing the levels of the ABT will increase the metadata persistence overhead, while reducing the expected recovery time, and vice versa. When adding child leaves to an existing leaf node, the information about which children are dirty can be obtained from the logical CBT. Since the user-perceived I/O performance is usually described as tail latency, we use the number of nines of the LSA to control the summary levels of the ABT. The periodical adjust procedure decides whether to add or delete leaf nodes in the ABT according to the statisticals of the last period. The period is configurable and by default set as 1 second. If there are too many metadata writes compared to the SLA in 1 second, then we will remove all the children of the parents that has experienced the most metadata writes during 1 second. Otherwise, we will add children to the leaf node that has experienced the least metadata writes during 1 second. Since the ABT is synchronously updated for every write request, the leaf nodes in the ABT has no false negatives for dirty states. That is, when a leaf is not dirty, each of the blocks is represented are guaranteed to be not dirty, and we can safely skip these blocks in crash recovery. Therefore, the recovery procedure of MapperX is straightforward. For each dirty leaf node of the ABT, demotes all SSD cached blocks of it to the HDD. In order not to introduce extra storage overhead, we reuse DMCache's 4-byte 30-bit metadata structure for each cache block, of which DMCache uses only the last 2 bits, a dirty bit and a valid bit, leaving the first 30 bits available for MapperX. We organize the first 30 bits of all cached blocks metadata structures into a flat bit array. To minimize the update overhead of adding or deleting leaves, we store ABT as the virtual ABT or VABT, which has the same number of levels and leaves as the CBT, but where only the ABT's dirty leaves are 1 and all other inner leaf nodes are 0. We use the flat bit area for statically representing the states of all inner nodes in the VABT. This is our evaluation results. The client runs the FIO benchmark tool to perform random writes that all hit the SSD cache for 300 seconds. We first compare the latency of random writes of MapperX and the DMCache. We use beta to represent the expected ratio of metadata writes to all writes, where beta is 1/10 to the power of n, where n is the LSA. The original DMCache adopts an asynchronous metadata update. The results show that the latency overhead of MapperX slightly increased, but the overhead is small compared to the original DMCache. In addition, we compare the recovery performance of MapperX and the original DMCache using the public I/O traces. We present MapperX, a novel extension to DMCache that uses an on-disk bit tree to synchronously persist the 30-bit metadata in a hierarchical manner. Experimental results show that MapperX significantly outperforms DMCache in crash recovery times, while only introducing negligible metadata right overhead. Thank you.